In the previous video, when we split the domain of the parabola, we split it up into equal pieces. For example, when we split into two pieces, we took something like this. When we split it up into three pieces, we took something like this. So here, this quantity is nothing but 2 divided by 3. And this quantity is 4 divided by 3. And similarly, when we divide into 4 pieces, we took 1 and a half, which is equal to 3 by 2, and this is equal to 2. Similarly, when we took 5 pieces, again we split into equal pieces. So the length of each of these pieces is equal to 2 by 5. So it's 2 by 5, 4 by 5, 6 by 5, 8 by 5, and 10 by 5, which is equal to 2. In general, if we were dividing the interval into n pieces, we took the size of each of the interval to be 2 divided by n. However, there was no reason why we should split the interval into equal pieces. We could have split the interval 0 to more generally, like something of this fashion. Okay, this is also splitting the interval 0 2 into 1, 2, 3, 4, 5 pieces. Okay, but the intervals do not have the same length. That is the only difference. So here, let's say this is x1, this is x2, this is x3, this is x4. So in general, any partition is given by some number of elements in between 0 and 2, in between the two endpoints. So if we specify 4 points in between the two endpoints, then that splits the interval into 5 pieces. That's something you have to observe. So we'll use this to define a general partition of an interval AB. Partition of interval AB. A partition of an interval AB is an ordered set P, which is equal to x0, x1, etc. up to xn minus 1, xn, such that A is equal to x0, is strictly less than x1, is strictly less than x2, is strictly less than etc. up to xn minus 1 is strictly less than xn, which is equal to P. These n plus 1 points split the interval into the following subintervals. I1 is equal to x0 to x1, I2 is equal to x1 to x2, etc. up to In is equal to xn minus 1 to xn. Because of this, we might also denote the partition P as the set xi minus 1 to xi, where I is going from 1 to n. Given a partition, we can define the norm of the partition. The norm of the partition P, denoted as norm P, is equal to the maximum of x1 minus x0, x2 minus x1, etc. up to xn minus xn minus 1. Notice that what we were achieving in the previous video by increasing the number of partitions was actually decreasing the norm of the partition. As n was increasing in the earlier, as n increased, the norm of the partition became 2 by n in that video. And so because of this, the norm was tending to 0 as n tended to infinity. After partitioning the domain of the function a comma b into subintervals, we took an arbitrary point in each of the subintervals, let's say ti, and evaluated the function at these ti's, say f of ti. And we assumed that the function takes constant value f of ti in each of these subintervals. And this is how we approximated the area under the graph of the function f. So it was not enough to just partition the domain into subintervals, but we also have to choose some special points from each of these subintervals. These points will be called tags. More precisely, if a point ti is selected from the interval ii, then the points are called tags. And a set of ordered pairs p dot given by xi minus 1 to xi comma ti, I going from 1 to n, is called a tagged partition. Of I. Given a tagged partition, we can find the Riemann sum of a function f from ab to r and a partition p dot defined as s of f comma p dot is equal to summation I going from 1 to n f of ti into xi minus xi minus 1. Here notice that these quantities f of ti into xi minus 1 is the area of the rectangle that we had marked in each of the subintervals. So f of ti is the height and xi minus 1 is the width of the rectangle. And so the product of the height and the width gives you the area of the rectangle. And this is the sum of the areas of those rectangles. And that is called as the Riemann sum for a function f and a partition p dot.